course, I could rearrange this and solve for temperature as well. You could also be asked for the amount of heat exchanged. All right, little math question. Let's see. If MC is large, what is the limit? MC approaches infinity of keep in mind that the mass flow rate will also affect the transfer coefficient. So yeah, right, you might think it goes to 1. Okay, so let's say it goes to 1, and then I come up here, and 1 minus 1, Q is equal to 0. Does that make sense? If I have a large amount of mass flow rate of cooling fluid, I'm not going to get any heat transport? Why? So you're thinking of it like you're minimizing contact time between the reactor and the flowing.
If you have a lot of mass and it's the same area.
Yeah, if it's flowing too fast, there's
really
no heat transfer. Yeah. So there's another thing that we can do though with this. Is you can represent this as a Taylor series. Did somebody say that? Well, I'll just put it there. And when x is small, then the first term is sufficient, or the second term, the first two terms are sufficient. And so when x is small, if this is small, which is another way of saying MC is large, this becomes 1 minus UA over MC CPC. And so if you plug that in, you get a simpler equation, which is often good as a first approximation. So you get Q is simply equal to and that's also because a large MC means the inlet temperature for the cooling fluid is approximately the same as the outlet temperature. Right. So that's kind of what you were thinking of earlier, right? If it flows really fast, then the temperature won't change that much. It doesn't mean that you're not transferring heat.
Yeah.
It just means that the temperature doesn't change. Okay, so again, this equation is valid when you have a large flow rate of your cooling fluid. Otherwise, this one's not that harder to compute, right? Okay, so any questions about the CSTR? All right, let's consider now a PFR. So the temperature now varies, right? At the inlet, we have one temperature. At the outlet, we have another. This isn't like a CSTR where the temperature is constant throughout the entire CSTR. And so that also means that Q varies. And so if I have some region of my CSTR where I have a heat transfer area, so imagine that there's a jacket here, again, core shell type, and I have a heat transfer area of dA, so some differential area. Q is equal to the integral so we're assuming here that within a very small differential area, A, the cooling water or heating water temperature is constant, and so is the temperature here. So it's very small changes, a very small section. And so that's where you get this integral form. And so then you can relate this to something we care more about. So instead of area, we want volume. So the cross-sectional area, or the heat, not the cross-sectional, sorry. The heat exchange area, which is distinct from the cross-sectional area. So AC, we always put that C, and this meant cross-sectional area. This is not that. This is the inside of your ring, It's that little annular region. It's not annular. I don't know what the word is. Anybody know?
It's the area.
It's a tiny little cylinder, right? But it's the heat exchange area. It's not the cross-sectional area. It's the heat exchange area. And so area divided by volume. Yeah, it's the surface area. That's a better way. Surface area of the pipe over a small region. So you get, here's the formula for the surface area of a cylinder is pi times the diameter times length. The volume so I can put that back into the integral because there's a form that I care more about. And Jason defines this, I think this book does too, as little a. We put that back into here, and now we're integrating from 0 to volume. So that's A, that's where it comes from. It's not a subscript. I'll try to write it big. So that A is a subscript, that A is not. Sorry. And so we don't have to put it in the integral form, we can put it in the differential form too. In the differential form you just get Okay, any questions here? So those are the equations for the the energy balances on the heating or cooling stream, not on the reactor itself, right? That's why we don't have things like delta H or reaction and stuff like that. All right, so let's go back to a CSTR. So start with our design equation. So for a CSTR, not a differential, volume is equal to the flow rate times conversion divided by the rate. Rate equation is now a function of both temperature and concentration. All right. So if we have a liquid phase first order reaction, then the inlet concentration is the inlet flow rate divided by the inlet volumetric flow rate. And concentration is simply FAO times 1 minus X over FA naught.